Today we continue the discussion of IO model. Last time we saw a few results on sorting, and we also saw a lower bound for sorting. And essentially we saw that for the permutation problem, we have the lower bound, and if I just ignore this branch is in fact a sorting lower bound. And we could also see algorithms that achieve this sorting bound. A summary of the result that we have seen so far, except for the searching one, is as follows. Over there. I'm not going to read this table. I guess you could also go back and watch the previous videos. Important thing here though is that permutation, which is trivial in the internal memory, is actually more complicated in the external memory. Now we move on to searching. Searching is obviously a very fundamental problem, and one of the most common data structure that is used for searching is a binary search tree. So I guess everybody's familiar with this. You have a bunch of keys, and let's say you compare with the value in that node. If it's small, you go to left. If it's large, you go to right, etc. And this data structure can do the following operations. It can also do, in addition to search, can also do a range search. In other words, after we find, let's say, node, we could also find all the elements in a given query interval in log base 2 of n plus t IOs or operations, if t is the output size. Okay, we want to basically improve this in the IO model. So these results are expressed in terms of internal memory complexity. Okay. How do we improve this? The idea is very simple. We can just use a basic blocking. Remember that in external memory, every block can hold b elements. So therefore, if I consider a subtree of this binary search tree that has height log base 2 of b, then the number of elements inside this block is exactly b, or at most b. So therefore, I could create blocks around this in this tree of height log base 2 of b. And the leaves will also be in one block, and in particular, if this tree is balanced, then you can see that the number of leaves in this subtree is roughly half of the number of nodes in that subtree. So therefore, if there are roughly b elements inside this block, there are roughly b over 2 leaves inside that block. So in other words, the leaves will also be very nicely blocked. What is the height of the resulting tree in terms of number of blocks? Well, the height was log base 2 of n, and every log base 2 elements are in the same block. So therefore, we just need to do a division, and we get log base b of n as the height in terms of block. So the block height of this tree is log base b of n. And we can also do range search with the same idea, because all the leaves are essentially in blocks very densely compact. In other words, if roughly b leaf consecutive leaves are in the same block, so therefore we can get this bound. So this is all very easy. The only thing we have not solved is the dynamic case, because typically search trees are most useful when we can in fact insert or delete elements to them or from them. In internal memory, for example, this is done using operations such as rotation. So if you remember a red-black tree, you have these kind of left-right rotations to maintain the balanced structure of these binary trees. However, it turns out that doing this idea in the IO model is complicated, and in fact it seems very difficult to do, because not only you have to maintain the blocking structure, you also need to make the leaves blocked as well, which looks very complicated. So the alternative is B tree, and in the next video we're going to look at what B trees are and a little bit of details about them. But before that, just very quick, there are many different variants of B tree. There are many different ways to slightly tweak them, improve them. So if you look at the literature, you'll see B tree, B plus tree, and etc. Like there are tens of different variations of B tree. So it's a very popular idea, and it's also a very fundamental idea.